Section 8.6, Electric Current. So when we refer to the motion of charged particles inside of a conductor, like a wire, we call that electric current. Most circuits, which are made up of metal wires, electrons are the things that are moving. It's the current that flows. When you're dealing with solids that conduct electricity, electrons are the things that are moving. In liquids, however, you can have positive ions, positively charged particles that move, and you can have then an electric current form that way. Because every metal atom has a bunch of electrons, and every piece of metal is going to be made up of millions and billions of atoms. There are billions of electrons just laying around inside of a metal like copper that we use for wires. And so there's always an enormous amount of electrons just available. And all it takes is a little bit of potential difference to nudge them, and you get them moving, and once you have those electrons moving, you have an electric current. The rate at which those electrons flow around in the conductor or the current is measured in amperes, or we just shorten it to amps. 1 ampere is equal to 1 coulomb of charge per second. So that would be 6.25 billion electrons moving past some point every second. So 1 amp of electric current is a lot. Most electric currents are much smaller than that. Now again, the speed of each electron as it moves through the wire is very slow. It moves really randomly in all directions. But what happens is there's just so many that they start to bounce into each other, and they push each other just a little bit along in the wire. So that even though each of the individual electrons moves relatively slow, about a centimeter every second, the signal that's in the wire travels at nearly the speed of light. It only takes one little bump at the beginning of the line, and the electron all the way at the end of the line feels that little bump and turns the object on. This is why when you flip the light switch, it comes on instantly, and you don't have to wait for it, regardless of how long the wires are. Because of this, you're not using up the electrons in the wire. The number of electrons in the wire doesn't increase or decrease. They just move through the wire over time. So the net charge on the wire itself is actually 0, even if there's current flowing through the wire. Just a couple of important things to remember as we talk about circuits in the next few sections. When we talk about charge, like electrons, we say that charge flows through a circuit. Electrons flow through a circuit. Voltage, which is a potential difference, is impressed across a circuit. So you place a potential difference across a circuit, and that causes the charge to flow through the circuit. Now, there are 2 types of electric current. The first is what's known as direct current, or DC current, and here you have charges flowing in one direction in a circuit. Batteries produce a direct current. You have a positive side and a negative side of a battery, and it produces a current in one direction. The signal in the wire flows through in one direction. Alternating current, or AC current, refers to charges flowing in alternating directions. So these are generated by things like generators, or the electricity you get at your home is known as AC current. In general, in the wires in your home in the United States, when you plug something in, the wall plug has a voltage of 120 volts and a frequency of 60 hertz. 60 hertz just means that it oscillates back and forth 60 times every second. So the direction of the current changes 60 times every second. We use AC current because we can step it up with things called transformers, which we'll talk about in the next chapter, and we can then send an electric signal a long distance without much loss to that signal.